Welcome, everyone, to the AMS Josiah Willard Gibbs Lecture. My name is Ruth Charney, and as president of the American Mathematical Society, it is my honor to introduce this talk. The goal of the Gibbs Lectureship is to increase awareness of the contributions that mathematics is making to present-day thinking and to modern civilization. Established in 1923, it is one of the oldest and most distinguished of the AMS lectureships. It is a pleasure to introduce this year's speaker, Professor Richard Baraniuk. Professor Baraniuk is the C. Sidney Burroughs Professor of Electrical and Computer Engineering at Rice University, where he also holds joint appointments in the Computer Science and Statistics departments. He received his PhD in 1992 from the University of Illinois at Urbana-Champaign and joined the faculty at Rice the following year. His research lies in the areas of signal processing and machine learning. His work has been recognized by a multitude of awards and honors. He is a member of the National Academy of Engineering and the American Academy of Arts and Sciences. He is a fellow of the National Academy of Inventors, the American Association for the Advancement of Science, and the Institute of Electrical and Electronics Engineering. In addition to his research, he holds over 50 patents, several of which are currently being used for medical and other applications. He is also the founder and director of OpenStax, a nonprofit organization which provides digital learning platforms and free open education resources. We are honored to have Professor Baraniuk as our Gibbs Lecture this year. His talk is entitled The Mathematics of Deep Learning. Please welcome Professor Richard Baraniuk.
Hello, everybody. Can you hear me okay? Okay, good. I tend to be a walker. I walk around on the stage, but in this case, since the screen is way over there, I'm going to try to stay right in place. It's just a tremendous honor to be here tonight. I am just really excited to be here to talk a little bit about some of the new mathematical theories that are emerging in this area of deep learning. And hopefully over the next hour, we can all learn something together, and this can be worth your while. I have just a quick logistical question. Is it best if we hold questions to the very end, or? Okay, so we're going to hold questions to the end, but I'm happy to discuss after the talk or outside. Okay, so let's jump in. We're in a very interesting time in mathematics today, as we, in certain areas, like signal processing, my own, we're moving from a world based on first principles type methods, based on, for example, physics in engineering type problems, to algorithms and methods based on data, right? And this is, these methods are rapidly eclipsing many of the methods that we've developed based on these first principles approach. And this is really going to be the subject of this talk. And we're going to frame this talk around thinking about function approximation in high dimensions. And what I mean by that is building some kind of model. So we have a function or an operator f that is taking our data x to maybe some inference about that data y. And this model f is determined by some parameters, right, that we're able to control. And this function approximation might be useful for many different potential applications. For example, we might have pictures of objects, and we'd like to classify whether the picture is a picture of a dog or a cat or a bird or a boat, right? Or we might want to slide Ingrid into an fMRI scanner and try to understand where she gets all of her great ideas from. Or we might want to synthesize from, starting from some random vector, synthesize a bedroom that actually doesn't exist in the real world and has never been seen before. And under this new paradigm, I think you could call it this, we're not going to think about building these Fs using some kind of physical or first principles basis. We're actually going to do this based on data. And we're going to use what are called deep learning algorithms or deep networks in order to do this. Let's get a quick show of hands. How many people here have heard of deep learning? Okay, that's a joke. Okay, so everybody here knows a little bit about deep learning or has heard about it. And the key idea here is that we're gonna learn the parameters of a deep network from training data, from a potentially large set of, in this case, this object classification case, a large set of digital images that have been pre-labeled with these yellow labels. And what we're going to do is we're going to use that data on the left in order to tune the parameters of this deep network in order to hopefully, when we have a new picture of a cat, we're actually able to classify it correctly as a cat. And like we just witnessed, everybody here knows a little bit about deep learning or has heard about deep learning. It's just kind of extraordinary how many stories have played out in the following way, that there have been 50 years of progress on a particular application based on first principles methods, and then along comes some upstart group that uses some training data that was available, and they just blow away the performance of these more classical methods. So it's tremendous empirical progress that has been going on in this field. This progress based on data, we might want to think about where it's going next. And in order to think about where it's going next, we might want to look, since the world tends to be cyclic, look into the past. And so let's go, I don't know, a few thousand years into the past, and let's go to Babylon, okay? Richard Feynman came up in the previous lecture. He's also talked extensively about this in one of his Feynman lectures. So the Babylonians were unbelievable mathematicians, and they were obsessed with data, and in particular with curve fitting, right? They fully understood polynomial curve fitting. They knew all the key theorems about what's required to do high quality curve fitting, and they were using it to predict astronomical events, things like eclipses, for example. And it's really kind of telling that the way they actually taught students to become mathematicians in this Babylonian world was not to talk about like general principles and theorems, but actually just to have them work out a whole bunch of problems, right, until they understood the general concept. Okay, that might kind of sound familiar. And as a result, they became great at curve fitting, but they were completely incapable of scaffolding together these ideas that they had to create something larger. So let's move forward a little bit in time to ancient Greece, right? In contrast, the ancient Greeks were obsessed with models, right? And the crazier, the better, right? For example, the sun and the moon and the stars, right? Where did they come? Well, they're there because there's a gigantic colander out in space with holes punched through it that sits between the eternal fire and the earth. And that explains not only the position of the stars and the sun, but also how they rotate, right, through the space. Crazy model. Nevertheless, this crazy model was sufficient for Eratosthenes, right, to be inspired to think about using geometry to actually deduce the radius of the Earth, right, to within about 10%. This kind of idea would have never occurred to a Babylonian curve fitter, right? Okay, so this talk is really about some Greek questions that we might have for our Babylonian deep learners, right? And in particular, there's been tremendous empirical progress on deep learning, but nobody really understands why it actually works. Like why? Why is deep learning so effective? No one is able to actually derive deep learning methods from some kind of first principles argument, right? It's just a black box model that's posited and then parameters learned from training data. And because of that, we have a big problem in the world of machine learning and deep learning in particular, is that we don't understand how these methods are failing when they're failing, right? And this can be very, very, very dangerous. And even more dangerous is the fact that we don't know how to fix sometimes these methods, right? So all of these questions kind of point back towards a starting point, and the key thing that has really made it difficult to answer these first 4 questions is that there's been a lack of a foundational theory for setting up and studying deep learning problems. Okay, and so what I hope to do today is just get everybody up to speed really quick on the basics of deep learning, and then talk about just one particular promising avenue for mathematical analysis that's been pursued by my group and some allied groups, and then talk about some applications along this avenue. So hopefully there'll be something in this for everybody. So let's jump in. So what is a deep network? The key thing about a deep network is hierarchy, right? It doesn't take an input X and create an output Y in one fell swoop. It does it as a composition of simpler operators, right? One of the critical things that makes deep learning so difficult to enter into as, say, a mathematician is that there's an incredible set of jargon that has been introduced, right? And hopefully today we'll be able to break through some of this jargon. We don't call these operators along the bottom that we compose together to create our deep network inference operators. We call them layers, right? But that's really all they are. We're just forming our overarching operator F by a composition of F1 through FL, where each one of those is called a layer. And these layers, at least in representative deep networks that really will help us understand what's going on in the general case. It's incredibly simple, actually, what's going on at a local level, right? And we can put it all just on this one single slide. So we have an input X, and we're going to define that as Z0, okay? And then we have an output we want to create Y hat. Well, we go through the first layer, which is our first operator in our composition, to create Z1. Okay, well, what is Z1? All we do, that's the second line of the slide here, is we just perform an affine transformation of Z0, multiply Z0 by a matrix W, add a bias vector B. So we just did an affine transformation. And then we do something very simply, or subtle, very simple nonlinearity. We pass that output vector through what's called an activation function, again, jargon, right? A nonlinearity that works independently on each component of WZ plus B. Okay, and this is called the activation operator, and a real classical method that's used all the time for the scalar activation function that's applied to each entry in WZ plus B is simply thresholding. Okay, and again, jargon alert. We can't. This is deep learning. We can't call it thresholding, so we have to call it ReLU, which stands for rectified linear unit. But all it is you do WZ plus B, and then you look at the output vector, and you just zero out all the negative entries in that vector. Does this make sense to everybody? Just tremendously simple. Okay, and then what do? You just do it again. And then you do it again and again and again. You do it L times, and that's what the equation on the bottom here is you basically just compose this very simple operation L times. And you might, at the output, you might, again, have a ReLU at the output, or you might not. And that's why I put that sigma star there. Hopefully this makes sense to everybody. Incredibly simple to describe on a local basis. So how do we actually learn? Oh, and actually let me just point out one really important thing. This deep net, it's an approximating operator. It has parameters, and the parameters are the W matrix entries in the W matrices and the B vector. Okay, so these are the parameters of our network, and these are what we need to tune, right, in order to create some useful input-output mapping. And we do this by optimization, and basically what we do is we bring in a training data set, and I'm going to talk about supervised learning here, just to keep things really, really simple. We bring in a training data set, and we feed where all of these digital images have been labeled, potentially by people, as to whether they're a dog, a bird, or a dog, cat, a bird, or a boat. And then what we do is we feed them through our network, and we see if there are errors. Okay, if there are no errors, then we're done. We have a network that can, given a picture of a dog, at least as far as our training data is concerned, will create the correct label. But invariably, we'll make errors. And so what we need to do is define a loss function. Right? Here we see that this first picture of a dog actually came out of the network as a cat. And so what we need to do is define an error, right? A loss function that tells us something about the loss between the dog label that is true and this cat label that is incorrect. You might even just think of the L2 distance, right? The squared error between those two labels in some suitable space. If you want to use information theory ideas, you could use a cross entropy. It all works out basically the same. So now you have an error that's going to tell you, an error measure or a loss function that's going to tell you how big your errors are. Okay, and what you're going to do is you're going to feed all of your images from your training data set through this network and compute this loss of your network. And then what we're going to do is we're going to optimize to try to drive down that loss. Now, something really important to bring up here, which is one of the really incredible difficulties in deep learning, is that even though you might use a squared error or a cross entropy loss function, which are naively convex, because of the nonlinearity in the network, these ReLU functions, this loss function is going to be extremely non-convex. Okay, so this optimization is not straightforward. Okay, so now what we're going to do is we're going to be naive, and we're just going to apply gradient descent to try to minimize this loss function by tuning all of the different parameters of our network, the W's and the B's. And we're going to do that in order to compute the gradient. We're just going to compute derivatives of this loss function with respect to each and every entry of the W's and the B's. And it turns out that since our deep net is a composition of simple operators, it turns out you can compute those gradients by flowing backwards through the network by chain rule. But again, it's deep learning. We can't call it chain rule. We have to call it backpropagation, right? But it's just simple application of this. And then we just do gradient descent, right? We take a gradient step that's in the direction of making that dog image closer to being labeled dog instead of cat, and then we repeat. Hopefully this makes sense to everyone. So this hopefully brings up some questions in your mind about whether all of this is really a good idea. And in fact, if you look at this naively, this is a crazy idea, right? First of all, we're not using physics or first principles to solve problems. We're just using data. But even if you're not bothered by that, we're using a very highly nonlinear approximation technique. And we're actually going to be working in a mode, I haven't really talked about this, but we're going to be working in a mode where we're extremely overparameterized, meaning the number of entries in the W matrices and the B vectors is going to be way bigger than the total number of training data points that we have, say images in our training data set. So you should just be thinking, wow, this should be incredibly ill-posed. Okay, and moreover, we just talked about we're going to have a highly non-convex loss function that we're going to try to optimize by gradient descent. Okay, but nevertheless, this works, right? At least empirically, this can work in a lot of different applications. And everything really came together in about 2012 in this perfect storm of folks introducing a new breed of deeper network architectures, not just 10 layers, but maybe 100 layers in these architectures. And then trying to get around this ill-posedness a little bit by going to enormously large training data sets. This is when ImageNet, a huge training database of labeled images, was released. And then we dealt with the fact that we need to do gradient descent based on these huge data sets and these huge networks. It turned out that folks figured out that you could use GPUs, graphics processing units, to perform these calculations rather than usual kinds of high-performance computing, right? And these GPUs came from the gaming industry, right? So these are the two sort of the three physical factors behind why deep learning really took off. And then the last is just also extremely important, and that is tens of thousands of researchers jumped into this area. And we have been going through an unbelievable alchemistic trial and error experiment for about the last decade of teams outcompeting each other on standardized problems and slowly notching the progress and performance up and up and up. And just to give you a sense of how incredible busy things are in this deep learning space, the conference, which is now called NeurIPS, which used to be called NIPS, in 2019, it actually sold out, if you can believe that. Okay, and they had to make it available to attendees by lottery. Okay, so these are conferences now where there will be 10,000 or more submissions to the conference, right, with maybe 2,000 accepted papers. Just an incredible trial and error experiment going on. Okay, not that alchemy is bad, right? What did it give us? Let me think: optics, calculus, gravity. And moreover, Newton did all of these things, interestingly, while he was sequestering himself in the countryside during the pandemic of 1665, right? So maybe alchemy, can lead us in some interesting directions, but then hopefully we can build a mathematical foundation, right, to support these alchemistic strides. Okay, so now, given this quick primer, hopefully it makes sense to everybody, we can describe what I would think is, or what I call the grand challenge of deep learning mathematics, which really all problems kind of come back to, and that is just really simple to state. And that is, it's incredibly easy to describe what goes on locally in a deep network. It's just a fine transformation followed by thresholding. Super simple. But it is not at all easy to describe what happens when you do this 100 times in composition, right? Not at all clear. So globally, what's going on is extremely difficult to understand. Nevertheless, of course, there's been folks who have been perfectly happy to just treat deep networks like a black box that is there to optimize. And there are, of course, worshipers of these black boxes that believe we're going to be taken to a higher intellectual level as a result. But what I encourage us to think about is how we can get back to foundations and to think about building a theory that could help us understand and then improve these deep learning techniques. Okay, so let's talk about one promising direction that some folks and my group in particular have been working on for the last number of years. And this avenue is thinking about deep networks as splines, as continuous piecewise affine mappings. This is the next bunch of minutes is work conducted with my students and colleagues from around the world. And we're not the only group working in this space. There's a cottage industry of folks now trying to think about piecewise linear approximation in deep nets. And we'll be touching on the results of some of these people as well in the course of the talk. So let's talk really briefly about splines, and in particular, continuous piecewise affine splines. So if you think of a spline approximation, in this case it's a one-dimensional problem, so a piecewise affine spline approximation is just taking this smooth dark blue curve and approximating it with some straight lines, okay? Straight lines that we want to be connect together. Right? These straight lines need to connect together. And you can immediately see as soon as we draw this picture that there's this yin-yang-like aspect of any spline approximation where we have, first of all, a partition of the input space, the x-axis in this case, into three intervals, right? A red, a green, and a blue interval. That's a partition. And then defined on each partition of the input space, a straight line. Right, a red, green, and blue straight line. Okay, and the key thing is that you need both of these in order to create a spline approximation. Okay, for people who know about splines, there's two key ways to create a spline approximation. The first is the really powerful way, where you allow the partition of the input space to be free. Unconstrained, and this is called free knot splines. this is going to give you by far the most powerful approximation performance. The problem is it's highly nonlinear and computationally intractable. It's very expensive even in 1D. In higher dimensions, it's not even clear how to actually do this. Okay, so people don't do free knot splines. They do some kind of easier approach, right? They might use a fixed grid, say a partition just on the integers, or they might do something really clever like wavelets. You can actually show that wavelets can be thought of like a really elegant dyadic grid type spline approximation. Okay, and deep networks are somehow in between. That's what we're going to see in between these two approaches. So the crux of everything that I'm going to talk about for the next bunch of minutes is that if you think about deep nets today, right? And when I say this, I mean primarily feed forward, but even a lot of feedback or recurrent neural nets that are based on standard architectures. There's a laundry list of architecture names up there, and standard layer types. There's another list of layer types based on activations like the ReLU that we already talked about, or an absolute value nonlinearity, different kinds of what are called pooling. It turns out that all of these layers that people are using so productively in deep learning today are all continuous piecewise affine operators. Very convenient, right? So that means that each of these blocks that we're composing together in our deep network is a continuous piecewise affine operator, and that means, it's really easy to see then, that those layers are CPA splines, right? They're spline operators. And since putting a spline output into another spline gives you another piecewise linear spline, okay, by composition property, a multi-layer deep network is also end-to-end simply just a continuous piecewise affine spline operator. Okay, so this is the key jumping off point for folks who are taking the spline view of deep learning. This is just a simple visualization of what's going on. In the bottom of this picture on the right, that's the two-dimensional input space. So our X, our input to our network, is 2D, just so that we can visualize it. You see it's been carved up into regions. And then up above it is the actual spline function, which you can see is composed of, in this case, planar, right, regions that are planes that are basically each defined on top of one of those partition regions. And you can really clearly see the continuity here of this overall mapping. This is exactly what's going on in even a 100,000 dimensional deep net with 1 million parameters. It's just we're in high dimensional space and can't visualize. Okay, so where things get really interesting for me at least is when we start to think about the geometry of this deep network partition. And so just to see where the geometry comes from, let's go back to a simple toy network. And let's just think of a simple one layer, just a single layer of a deep net. It's a two-dimensional input, five-dimensional output. And remember from our primer, what do we do in order to compute Z1, which is the output of the first layer? All we do is we take X, our two-dimensional input, we multiply by a 5x2 matrix W, we add a length 5 bias vector B, and then we process each individual red output here through this thresholding ReLU function, right? That's all we do. Well, if we write out what's actually going on in this matrix multiplication, focusing on just one of these outputs, right, ZK, okay, the middle one here, we can write, it's easy to write out that ZK, right, the kth output, is basically the input to that first layer, X, dot product, just inner product, with the kth row of the W matrix, right, plus the kth entry of the bias vector, and then process that through a threshold. If this number is Wx plus B is negative, set the output to 0. If it's positive, pass that number through. Okay, well, the key thing here is focusing in on this Wx plus B. We can use that to figure out how the spline partition of the input space is formed once we think about 5 units together and not just a single unit. And the key thing is realizing that Wx plus b is the equation of a hyperplane. Right? It's a hyperplane that's steered by W, shifted by B. Okay? And so now we see that if we have 5 units in the output of this particular layer, we will be putting down 5 different hyperplanes, in this case straight lines, in this 2-dimensional space, that basically separate the space in half. They cut it in half. On one side of the space, in this case, the lower part, this is where Wx plus b was positive, right? On the other side, the upper side, this is where Wx plus b was negative, and so the output is 0. Okay, and so basically what we have is, in this case, we have 5 outputs, we'll have 5 hyperplanes, and the spline partition regions are precisely these convex polytopes that are formed by the intersection of these hyperplanes. And it turns out that these are what is called a hyperplane arrangement. Okay, and so the way that the partition is generated is actually really quite straightforward, and moreover, you can actually develop really simple formulas for the affine transformation inside each one of these particular tiles, right? So we have closed form formulas for the affine transformation matrix A and the offset B for each individual one of these regions, okay? This seems like pretty standard stuff, okay? But these are not standard kind of splines, okay? And they're not standard kind of splines because of a dimensionality explosion that comes from intersecting K hyperplanes in some kind of input space. And in particular, if you just think of like ReLU-based networks, where you have an activation function here with 2 pieces, right? There's a horizontal piece and a piece with slope 1. Well, it turns out that if you intersect K of these, the corresponding hyperplanes in a space, you're actually going to generate up to R to the K possible convex polytopal regions, right? So an exponential number of regions, and which clearly grows enormously quickly, and this is with a single layer. And we might do this 100 times, right? And so the number of partitions in this spline approximation is just not like anything people have thought about when they think of spline approximation. It's kind of on the absurd kind of level. You might have a machine learning problem where you have 1 million training data points. You have 10 million parameters in your deep net. Okay, but that 10 million parameters, right, you're going to have 10 million to the, right, or 2 to the 10 million. So you're basically going to have a zillion, right, partitions, right, if we can define a new term, right? So it's, enormous numbers. So and it's hard to even look at these regions in a practical network. And so we actually developed a method to be able to look around in the input space, actually be able to visualize the spline partition. The tool is called Spline Cam. No time to really talk about any details today, but there's a link at the bottom of this slide where you can go grab the code to try this out. But it's basically an exact, really fast compared to previous methods, way to be able to put in a set of trained deep network parameters and then be able to generate the partition geometry along a particular low dimensional slice of interest. Okay, and so here's an example of a Spline Cam visualization. We trained a deep network with a few tens of thousands of parameters to tell the difference between 2 kinds of cats. Okay, and these 3 white dots on this 2-dimensional slice through our input space, these 3 dots are 3 of the training points. Okay, the red is the decision boundary, right, that distinguishes on one side tabby cats, right? Any picture that falls to the left and below of this red decision boundary is going to be classified as a tabby cat, and anyone that lives to the upper right will be classified as an Egyptian cat. And you can see the just enormous number of spline partition regions here in this in this deep network. Okay, and we'll talk about this in a second. Here's another visualization with this Spline Cam tool. A currently very topical area of application of deep learning is to create what are called implicit neural representations of data. And this tends to be lower dimensional data, like a digital picture, thinking about it as a landscape, right? Or a 3D object, right? Which is, you could think of as a 2D, locally like a 2D manifold in 3D space, like this bunny here in the lower left. And this is an example here of 3 different planes that we selected, the X, Y, and Z planes. X equals all of these planes with these entries equal to 0. And on the right, you see a visualization of the spline partition geometry of an implicit neural representation of this 3D object with in red, the actual boundary of the bunny in this case. And I probably didn't mention this, but we're actually able to trace exactly where the decision boundary, or in this case, the level set or the boundary of the object passes through in this input space. Okay, and so you can see a tremendous density here of hyperplane cuts around the object boundary that are creating a very fine partition around that spot. Okay, and so these 2 examples maybe point towards that maybe things are not as absurd. This idea that we have zillions of partition regions seems crazy, but maybe it's not so crazy if we think about things in a different way. Okay, the first thing that we take away from these just 2 visualizations is that most of the spline partition regions are empty. Right, they're just a tiny fraction of the partition regions of this spline approximation that are actually going to have a training data point in them. Okay, so that's weird, right? And that's something that might make us think in a different way. And the second, that's really a restatement of this first, is that most of the regions are very far away from the actual action. In the case of representing the bunny, all of the spline partition regions far outside or inside, in the inside of the bunny, really play no role in the representation or the further processing with this bunny. And it's only those partition regions that intersect the actual object boundary. So this gives us some hope that maybe we can think about spline representations in maybe a different way and be able to make some progress. The other thing that's really critical about these spline partitions, and that's what I'd like to turn to now, is that they have a tremendously rich multi-scale structure that comes from the fact that a deep network is a composition, right? It's a hierarchical composition of a number of simple operators. And so let's talk a little bit about that now. So recall what we mentioned at the very beginning, or not very beginning, but during the primer. And that is that a deep net layer is a continuous piecewise affine spline, but also the composition of 2 layers or 3 layers or all of the layers, right? So all of these operators from the input to anywhere else in the network is a continuous piecewise affine spline. And it turns out that the spline partition, as you go from a network with, say, 4 layers to a network with 5 layers, okay, what happens is the spline partition of the 5-layer network is formed by starting with the spline partition of the 4-layer network and then subdividing it in a way that we'll talk about now. Okay, so recall that there'll be a layer 4 network, right, has a spline partition. Now what happens when we lay on this 5th layer? And just to keep things simple here, let's stay in 2 dimensions, 2-dimensional input space, and just a two-layer network. So the output to the first layer of our 2-layer network, we'll have an input space, and then we'll have a number of cuts, right, hyperplane cuts. In this case, there were 6 output neurons or units, so we'll have 6 different cuts, and you see that these cuts form a set of convex polytopic spline partition regions. Now what happens when we go through 2 layers, the same first layer, but then add on a second layer? That second layer, with respect to its input, the input of the second layer, that second layer will do exactly the same thing. It will throw down a number of hyperplane cuts that divide the input space of that second layer into polytopic regions. But we're not interested in what happens at the input to the second layer. We're interested in the input space. So we actually have to drag those hyperplanes back through the first layer. And what happens is that causes them to fold. Okay, and so what happens is that the layer 2 hyperplane cuts, when you look at them from the standpoint of the input space of the entire network, are going to be folded whenever they cross an earlier layer's hyperplane cut. Hopefully this makes sense to everyone. Okay, and they're folded in a very precise way, okay, to maintain continuity of the mapping. Right? They can't just be folded arbitrarily, right? And this is, I think, an extremely interesting area of study. Okay, and so just thinking about this back to this toy example that we had earlier, right? So the hyperplanes are folded, right, by later layer hyperplanes are folded by previous layer hyperplanes, maintains continuity of the mapping. And that means that if we think of this particular green, either partition region in our input space or this plane that is our function output of our network, okay, the actual slope and offset of that plane is extremely constrained, right? It's constrained by the slopes and offsets from all of the previous layers, and also the weights and the biases of that current layer. Okay, and what that means is that there's actually, even though we have an enormous number of spline partition regions, the actual function approximation that can sit on top of those regions is extremely constrained to have a number of degrees of freedom that is far less than the number of regions. Okay, and since this is a talk where I'm hoping to invite as many of you as possible to join the deep learning theory crowd, I'm going to pose some invitation questions as we go through the latter part of this talk. And this is one of them, right? This is something that we don't understand, right? How does this parameter sharing actually really work, right? How does this dimensionality reduction due to the constraint of the affine transformations based on previous layer hyperplanes, how does this actually take place, and how does it regularize? This is the key thing, is that this is a regularizer for what would ordinarily be an extraordinarily ill-posed problem of actually fitting a spline to our data, right? We have way too many regions, okay? But what's going on is this continuity constraint is doing everything. So this is a very important, I think, open question. So hopefully somebody here will solve it. Continuing in this direction, let's think about a network that's doing classification, say two-class classification between, say, dogs and cats. Well, it turns out in a network like that, there will be a final layer. That final layer will culminate in a single output. There'll be a single hyperplane cut caused by that final layer. And we can pull that hyperplane cut all the way back to the beginning of the network, and it will basically fold as it passes through every previous layer, creating the actual decision boundary, right? The decision boundary starts at the final layer as a straight or flat hyperplane, but by the time it's pulled through to the input space, it becomes a highly contorted decision boundary, dogs on one side, cats on the other side. Okay, it turns out that you can actually compute the dihedral angles of this folding. Okay, so you can actually know, based on the A's and the B's and the partition regions, you can actually know whether this particular hyperplane was folding in a certain part of the input space really acutely or barely at all. Okay, and this, we believe studying this holds the really key to studying the smoothness of the decision boundary, which is extremely important from a theoretical perspective in machine learning, because it's the smoothness of the decision boundary tells you a lot about how the classifier in this case will generalize, how well it will work on pictures of dogs that aren't in our training set, for example, and also the robustness of our classifier, right? So this, again, is a big open question to study the decision boundary through this dihedral angle theorem. Another interesting direction to think about is the connection to computational geometry. If you think about how we form our spline partition, it's a hyperplane arrangement that's formed from the intersection of hyperplanes. That's going to generate convex polytopic spline partition regions, but it turns out they're even more beautiful than that. It turns out, for all of these deep nets that we've been talking about, it turns out that their spline partition regions are what are called power diagrams. Who's heard of power diagrams? Yeah, it's a bit esoteric, but everybody's heard of Voronoi diagrams, probably a lot more people. Okay, so what's a Voronoi diagram? It's a set of centroids, and then what you do is you associate, put centroid, in this case, put some centroids, dots down in the plane, and then build a tiling by associating a point in the plane with its closest centroid, according to your favorite distance metric. Okay, say two distance. Okay, that's a Voronoi tiling. Okay, well, it turns out a deep net doesn't have a Voronoi tiling partition region, but it has what's called a power diagram partition tiling, which is an extension of the Voronoi tiling, where we have both centroids and then what's called a radius, which is like a biasing that can change, basically change the local geometry of the Voronoi diagram. And a really interesting open question in this direction is to connect these power diagrams to a whole host of related areas in signal processing, information theory, machine learning, things like vector quantization, optimal quantization and sphere packing, the idea of clustering. All of these are connected with Voronoi and power diagram tilings, and there are probably some really interesting connections also here with deep learning. Okay, so that's, let's just summarize where we are so far, right? So the story up to now is that deep networks, you can think of them as a tractable way to do spline approximation in very high dimensions from samples of a particular function, and they somehow sit between the idea of a fixed partition and free knot splines. And the tractability comes from this composition, the hierarchy, the fact that we're using layers to create this spline partition and using subdivision. That's really the key. That's when neural networks really took off, is when performance-wise, is when networks became deep, when we really started exploiting hierarchy, and that's also exactly what's going on here, why the spline fitting is so tractable. So that's what we know so far. So let's look at some quick applications with the time remaining of applying some of these ideas. And let me get a quick time check. Do we have about 5 minutes or 10 minutes, or what do we have? Okay, so let's just do some quick applications, and then I can take some questions. So the first that we'll talk about is comparing deep network architectures, right? Architecture 1 versus architecture 2. Can we compare them theoretically and not just architecture A seems to work better than architecture B? Okay, so there is a menagerie of different architectures out there. Here's some buzzwords: convnets, ResNets, dense nets, right? And really, this idea of what's called ResNet was really a huge step forward in deep learning. Okay, a convnet is exactly what we've been talking about up to now. Exactly. The key thing is you make these W matrices convolution matrices. Okay, and that they were the state of the art starting in 2012. But then a number of years later, somebody had the idea to say, well, wait a minute, let's also put some skip connections. so that our input can go through the layer, but it can also skip around. Okay? And this is called a residual connection. And what folks found is that these work really well in practice. There is absolutely no theoretical reason from an approximation standpoint about why you would prefer ResNets over ConvNets, right? If you have enough parameters, they both have universal approximation capability. But in practice, ResNets work better. Well, what do I mean by that? Learning works way better. Gradient-based learning. Okay, but nobody knows why. Okay, there was some really interesting empirical work, right, into trying to attack this question of, it's not what a deep net learns to approximate that matters, it's how it learns. And the empirical work from Tom Goldstein's group at University of Maryland was that the loss landscape, the loss surface or loss function of a ResNet is just way smoother and nicer than that of a ConvNet. So these are low-dimensional slices through the high-dimensional loss surface of two high-performing networks. Which one would you prefer to find the bottom of? Right? Clearly, it's the ResNet. But there's no theory to explain this. Okay, well, it turns out that it is straightforward to attack this question using this spline approach. So the first thing we'll do is we'll define a spectrum of deep networks by taking what we talked about in the primer and then just adding on this red term at the end, rho times z. This is this residual or skip connection. When rho is 0, it's a standard ConvNet, like we were talking about in the beginning. When rho is 1, it's a residual network. Okay? And what we're going to do is study the loss surface as we change rho. Right? How does the loss surface change? And we're going to focus on squared error loss. Turns out you can do all of this with cross-entropy loss, but let's just focus on squared error loss. Well, it turns out, if you just think about it for a minute, that since the input-output mapping of a deep net is a continuous piecewise affine spline, well, if we're using a quadratic loss function, then the mapping from the parameters, the w's and the b's, to the loss function is going to be piecewise quadratic. Okay, so the loss function is just going to be a piecewise quadratic loss function, little pieces of bowls, and our goal is to find the bottom. Okay, and the great thing about piecewise quadratic is that we can do local quadratic analysis, right? And we know that the local geometry of this piecewise quadratic loss function is going to be determined by the singular values of the Hessian matrices, right, at each of these local pieces, which will be determined by the W's and B's, rho, training data, and the spline partition region. But the thing we're interested in is rho, okay, fixing the W's and B's. Okay, why is this important? This is important because if the condition number is really bad, that means locally the loss surface is really bad, right? Really eccentric, really hard to get to the bottom of, right? So we'd like to have a small condition number rather than a large condition number. Okay, 2 theorems. Turns out you can prove, okay? And my colleague Rolf Rietti actually derived a whole new branch of matrix perturbation theory in order to do this. It's just really beautiful, of independent interest. But he was able to use these methods to show that in the case of rho equals 0, the condition number of this local loss function is not bounded. So the loss surface is terrible. Whereas for ResNets, even as soon as rho gets above 0, doesn't have to go all the way to 1, that you immediately have bounds, closed form bounds on the condition number of the loss surface, right? Which tells us why, right? Gives us the theoretical justification of why the ResNet loss surface is less eccentric and local minima that are much more accommodating to gradient optimization. So this is just one quick application, but there's so much more to be done, right? An invitation question is how now can we use this understanding to actually come up with better learning algorithms, right? Momentum, different ways to find the bottom of this loss surface, or even better network architectures. Can we learn these based on, or develop these based on this better understanding of this loss surface? Lots of work to keep doing there. Let me talk about just one last application, and that is understanding what's called batch normalization. And this is well, let's just talk about batch normalization. So it turns out in the deep nets that we have talked about, let's call it like the vanilla deep network, they're described by the first equation on this slide. Okay? This is basically just operating each entry of the output separately rather than with the matrix W. But just recall that we produce the output, right, of layer L, ZL plus 1, simply by taking the inner product between the corresponding row of W and Z, right, row of W, and then we add B. This is actually not what's done in practical deep nets, right? In practical deep nets, people use what's called batch normalization, which is a kind of a data centering procedure, okay? And basically, they use the second equation. And we're going to ignore the gamma and beta parameters of batch norm. It turns out they don't actually do very much. The key parameters are this mu and this theta. Okay, so you see what we've done is we're still doing W inner product Z, but then we're subtracting off this mu from every output, and then we're normalizing or dividing by this theta. And where do the mu and theta come from? Well, the mu is just the mean of W times Z for some collection of training data. So it's like a mean of our WZs. Okay, and what is theta? That shouldn't be sigma, it should be theta. It's like the standard deviation of that data. Okay, so it's like a centering. If you do PCA, you would do a similar kind of centering. This is used all the time, okay, but just totally not understood, right? Nobody really knows what batch normalization actually does. But it turns out if you take the spline viewpoint, it's clearer what it does. Okay, well, let's talk about mu. Well, what does mu do? Mu translates the hyperplanes. That should be kind of obvious if we go back here, right? Because mu is like a bias term, right? It's going to W will steer the hyperplane, but mu will steer it, okay? And so what mu does is it steers the hyperplanes, but it doesn't just, or not steer, it doesn't just translate the hyperplanes. It actually does it in order to minimize the total least squares error between each hyperplane and the training data. Okay, which is kind of cool. So it's doing a total least squares optimization. Okay, and it also transforms the spline partition into what's called a central hyperplane arrangement, meaning all of the hyperplanes intersect, right, in the center, in a center point of the space. Okay, so that's what mu is doing. Okay, what is theta doing? And I realize I'm using sigma again here. Sorry. But what is this theta or sigma parameter doing? Well, it folds the hyperplanes. Okay, it folds the hyperplanes. When you have more than one layer, the sigma of the layer after the first layer is going to fold the hyperplanes again in order to minimize the distance between that particular hyperplane and the data. Okay, so what we see is that both mu and sigma, or the theta that I showed earlier, are trying to pull the hyperplanes towards the data. And what that does is that creates a much finer approximation of our spline closer to the data. The action is near the training data. And if you just look at the first row of these images, these are just the partitions from one layer 1 and 2, layer 1, 2, 3, layer 1, 2, 3, 4 of a toy deep network. And you see that the partition in the upper right corner is just kind of like random, right, with respect to the data. Whereas in the lower right corner, you see the hyperplanes have all been drawn towards the training data. And we have a lot of very skinny, right, partition regions that are aligned along the data manifold. That's going to create finer data approximation and higher performance and more stability in your approximation. Okay, so that's been really fun to look at batch norm. Okay, where we haven't been able to make progress though, and an invitation question, is can we actually prove that this batch norm equipped network is actually going to provably perform better than one without batch norm, right? That's a big open question. Okay, last thing I just want to mention is approximation theory. So a big invitation question is, do we know anything about how well deep nets perform as a function of the number of parameters in the network, and how does this compare to classical results, say using Fourier methods or wavelet methods? Okay, well, it turns out that a lot of progress has been made. Okay, so it's very exciting. There's a paper came out in the last year that I highly suggest you check out, where Ron DeVore and his collaborators have actually been able to show superconvergence, so faster than any classical approximation, linear or nonlinear approximation technique, at the expense, however, of potential instability in the approximate. So lots of interesting work still to be done here. Okay, so let's wrap up. I hope everybody took something away from the talk, whether it's from the primer or from the spline part or from more philosophical aspects. What I hope you take away with, though, is splines, and in particular continuous piecewise defined splines. They really provide a firm foundation for developing a theory of deep learning that we can really build on. There's no question that deep learning, at least from an empirical standpoint, the driving concepts are here to stay, at least for the foreseeable future. It's ideas of overparameterization, non-convex optimization, big data for training. But we and the folks in this community think that the idea of thinking about partitions and then thinking about highly constrained piecewise defined approximations on top of those partitions are a really powerful way to try to study these ideas around non-convex optimization, overparameterization, et cetera. With that, I'd like to end, say I invite questions, and thanks again so much for the invitation to speak today. Thank you.
Yeah, that was a very interesting and thought-provoking talk. I think a lot of people have to leave, so we're not going to have open questions, but if anybody wants to come up, and there's not another lecture in here, so if you want to come up and talk to Professor Baraniuk up here, you're welcome to. So let's just thank, once again, Professor Baraniuk for a great talk.